All right, next we're going to look at conditional probability. Conditional probability is written with a slash. Kind of looks almost like B divided by A or A divided by B. The conditional probability of B given A. This slash right here is read as given. So the formula for conditional probability of A given B, you can see down bottom here. The probability of A given B equals the probability of A and B divided by the probability of B. And we have it written out three different ways. A and B, A intersection B, and then in words, which might even make things more easy, is the probability both events occur divided by the probability that the given event occurs. Now, if we wanted to do the probability of B given A instead of A given B, that's fine. It would be the probability of B and A always divided by the given. In this case, A is given. Well, let's put some context to this conditional probability. It's a probability that one event occurs given that the other event occurs. So if we look back to the gender and your ear pierced table from previous problems, I think that you'll be able to see how conditional probability works. So, whoops. There we go. So let's say, what's the probability that your ear is pierced given that you're a male? What's the probability your ear's pierced given that you're a male? You guys are all looking at the table right now telling me, oh, that's easy, man. It's 19 out of 90. Absolutely. So the probability that your ear is pierced given that you are a male. So given is a male, we're only looking at males. None of this stuff makes any difference for this problem. So the probability you have your ear pierced given you're a male. So the denominator is 90. It's no longer out of 178 because now we have a condition put onto the probability. The probability that your ear is pierced given that you're a male. So it's out of males only, and of those, 19 have their ear pierced. Pretty simple. Well, why do we need this crazy formula down here? Because we won't always have a two-way table. It won't always look this straightforward and simple. Let's look at how the formula works for this. If I wanted to find the probability that my ear is pierced, given that I'm a male, that's equal to the probability that my ear is pierced and I'm a male, divided by, always divide by the given, so the probability that you're a male. So the probability that my ear is pierced and I'm a male. So let's look at this. Ear pierced, and male. Oh, that's 19 out of 178. Divided by the probability that I'm a male. The probability that I'm a male is 90 over 178. Now I need to divide these two fractions. 19 178ths divided by 90 178ths. Well, remember when we divide fractions, leave, change to multiply, and flip upside down. Well, the 178ths will cancel, leaving us with 19 over 90. No surprise, that's the answer we got by just looking at the table. So conditional probability, the probability of A and B divided by the probability of what's given. Let's look at another example real quick. So let's say I want to know the probability that I am a female given that my ear is not pierced. All right. Well, the probability that I'm a female given my ear is not pierced. So given is that I do not have a piercing. So I'm looking at this. How many individuals do not have piercings? Oh, 75. That's the given, the denominator. Of those 75 who do not have an ear piercing, how many of those are females? Oh, that's 4. So the probability I'm a female, given I do not have my ear pierced, is 4 out of 75. Let's once again see how this formula works. The probability of female given that my ear is not pierced. So that's the probability of female and my ear is not pierced, divided by the probability that my ear is not pierced. So female and not pierced. Female and not pierced. Not female. Oh, that's 4 out of 178. The probability my ear is not pierced. Not pierced. Oh, that's 75 out of 178. Using our rules for dividing fractions once again, we have 4 over 178 divided by 75 over 178. Flip the back number upside down, the 178s cancel, and we're left with 4 over 75, which is what we knew the answer was going to be just from looking at the two-way table. Conditional probabilities, the probability that one event occurs given that the other event occurs. Right. And conditional probability, oftentimes we want to use a tree diagram to model. Now, conditional probabilities is given one thing, or the probability one thing happens given that another. So it's kind of like a sequential event. Whereas Venn diagrams are what's the probability that this and this happen at the same time. So when it's one and the other simultaneously, we want to use a Venn diagram. When it's sequential, the probability that this happens given that the next event happened, then we want to use a tree diagram, which we'll look at here in a moment. Okay, so we have the general addition rule that we talked about earlier, which said the probability of A or B equals the probability of A plus the probability of B minus the probability of A and B. That works always for every single problem in the world. That formula will work for any union of two events. Remember, the union is or this event or this event. Now, you can see up at the top here, we're going to talk about independent events. Previously, we spoke about mutually exclusive events. Mutually exclusive means they have no outcomes in common. Independent events means the probability of one event occurring has nothing to do with the probability of the other. What is the probability that I flip heads given that you ate a grilled cheese sandwich? It's still 1/2. It doesn't matter what you ate for lunch. The probability of me flipping heads is never going to change. Well, if two events are independent, then they will follow certain rules. Whoops. So if two events are independent, independence means the probability of knowing that the probability of one event does not change the probability of the other. So given that one event occurred, will not change the probability that the next event will occur. So the probability, if two events are independent, then the probability of A given B is equal to the probability of A given not B. It doesn't matter what B is. So if the events are independent, then the probability of A given B will just be the probability of A, because it doesn't matter that you ate a grilled cheese sandwich. The probability of me flipping heads is 1/2. Okay? Same for the other way around. The probability of B given A would be the probability of B, if and only if the two events are independent. Another way to show independence or check for independence would be if the probability of A and B equals the probability of A times the probability of B. This would also show independence. So we could prove independence this way using the probability of A given B equals the probability of A, or we could prove independence with the probability of A and B is equal to the probability of A times B. Those are two ways to determine, are these events independent? Oftentimes, we'll have to determine independence just by the situation, like my flipping a coin and you eating a grilled cheese sandwich. Very obvious that those two rules are independent. Okay, we said that multiplication was and. Okay, so if the two events are independent, then this is the formula for and. Because the probability of A and B is the same as the probability of A times the probability of B. Okay? But if the events are not independent, if they are not independent, we must use the general rule. Remember in probability that the general rule always works. So you can see this formula right here. The probability of A and B, or A intersection B, equals the probability of A times the probability of B given A, if they are not independent. Why does that formula work if they are independent? Because the probability of B given A is just the probability of B when the events are independent. The general rule will always work. Okay? And you can see the multiplication rule for independent events down here. These formulas are extremely important. They will, most of them or a lot of them will be in your formula packet, but I would highly recommend that you put them down into your guided notes and then maybe write them a few times. They're extremely important for what we're going to do in probability. All right, so we looked at union of two events. We looked at the intersection of two events. We looked at the complement of an event. We looked at multiplication for intersection. We looked at addition for union. We need to know, what does it mean to be independent? What does it mean to be mutually exclusive? And what is this idea of conditional probability? Super important. Not a whole lot in this chapter, but a lot to think about. So practice. You need to do a lot of these problems before you're going to feel comfortable.